Well, welcome to this. I'm going to be going over the contents of my book, Mastering Python for Bioinformatics. To get started, you'll need to go to my GitHub page. It's one of my pinned repositories. It's called BioFX Python. And if you click on this, you'll be able to go over here to the code section. You will be probably using the HTTPS protocol to download this. I will be using SSH. I'm going to copy this URL to my clipboard. I'm going to go over here to my terminal. I'm going to go into a work directory. I have previously checked this out, so I'm going to remove it. And then I'm going to use git clone with that URL to bring down the code. That is going to clone it into my local directory. And then I'm going to go into BioFX Python here. And you'll see the directory structure here, and the first thing I'm going to do is to set up a virtual environment that will help me to manage Python and the dependencies here. This is not something that I cover in the book because I'm using some tools that didn't exist at the time. I'm going to be using UV, which can be found here from astral.sh, and there are instructions for installing UV. And I'm still a little bit new to this, so I'm going to stumble through how to set it up to show you. I've used it on a few projects and it seems to work really well. In here in this requirements.txt file, if we cat that file, we see that there are a few modules that we'll be using here. One of the most important ones is going to be BioPython. We also talk about Python testing with pytest, and a few other modules. So normally you would do a pip install with this, and if you are able to do pip install, then you're just happy. Go ahead and do that. It'll be just fine. A lot of times there's a lot of problems with installing Python and dependencies, so we're going to use a virtual environment. And for that, I believe the first step I need to do is to, after I've installed UV, is to create a VNV, virtual environment. And so it's going to create in a hidden directory here, .venv. There's going to be a bin activate script that I'm going to source in order to activate this. So let's give that a shot. Sourcing that, and now I'm going to use UV pip install the requirements file to install all the required the dependencies that I have into this local directory. As you see, it is working and works pretty fast on my machine. While we're letting that happen, I will say that you can also pull up the book. I'll be covering chapter 1 here. So we have now installed the dependencies, and if I say which Python 3, I'm hoping it will be 1. Yes, that is installed into my virtual environment. So when I now run Python 3 with my scripts, I'm actually running the one that's in this virtual environment, and I have all the dependencies installed. So hopefully that goes smoothly for you. So let's get started. We're talking about the very first chapter here is counting things, and we're going to be using the Rosalind DNA challenge. So if I click on this, it's a fascinating little problem. Given a string of DNA, just a string, no fancy formatting here. Given a string, we want to be able to count the numbers of A, C, G, and T that occur in that string, and the output should be each one of the numbers for A, C, G, and T separated by a space. And the nature of Rosalind is that you can write these solutions in whatever language you want, and it doesn't matter because just given a certain input, you're expected to have a certain output. And they give you pretty simple inputs to start, and then when you think you've solved it, you log in, and they give you a much larger data set, and then a very limited amount of time to solve it, to prove that you have written a program that will do it. So it's a lot of fun. I've taught myself a lot of skills by going through these challenges, and I recommend that as you're learning new languages, you come back and try to write more solutions in these. So we are going to learn a lot of stuff in this chapter. The first thing is that we're going to start off using new.py, which is one of the dependencies that just got installed here. That is going to create a stub of a program that uses argparse that we're going to use to parse the command line arguments. We're also going to be talking about how to use pytest to test our program. And then we're going to be talking about how to iterate over the characters in a string, ways to count things in strings and other kinds of collections, how to create decision trees using if and else if, and how to format strings. So quite a bit to get through here. So the first thing to do is to go into the O1 DNA directory. And I'm going to be probably a lot of this, I'll be showing you how I code, which is just in the terminal using a text editor called VI. If you're more comfortable using something called an IDE like VS Code, you're welcome to do that. And in some of the exercises, I may show how to use those tools as well. But I've been coding for a long time, and this way works for me very well. So the first thing I want you to do is if you do an ls, you'll see that there are a number of existing solutions here. And we are trying to write a program that's going to be called dna.py. So the first thing to do is just to copy the solution 1 to a program called dna.py. That's going to be important because for the testing is going to be looking for literally dna.py. So with that, I should be able to execute the program by doing /.dna. And if I do that, I just, with no arguments, I should get a help message. Now, this is one of the most important things that I always teach, is that programs should provide documentation about how they work. So I should never ever have to open up the source code to a script to figure out what its arguments are and to change things to make it work on my system. Anything that is variable about a program should be an argument or some configurable aspect of the program. You can have README files that describe all the information about your program, but those are easy to get out of date. So it's much better for the program itself for the documentation to be integrated into the program. So here's how the program should work. So if I run this program and give it a string, and I'm going to give it 1A, 2 C's, 3 G's, and 4 T's, so that I should see 1, 2, 3, 4. If I give it that, not enough T's. 1, 2, 3, 4 is the output. So that is the way how the program should work. If I jump over here and grab the string from Rosalind and run it with that, I get 20, 12, 17, 21, 20, 12, 17, 21. So this solution appears to work just fine, and we will be looking at that. There is also under here, if I run tree, which is a little program that you may need to install. It's not normally installed, but it shows me that there is a test directory. Underneath that is a script that I've written that has a bunch of tests called DNA_test. So DNA is the program that it's testing, and _test tells pytest that this file contains tests. And then there are, under the test directory, several input files. And if I use the cat program for concatenate, and I say cat tests inputs input 1, you'll see that that is the contents of that file. And so the reason that these input files exist is because I want to test my program with known inputs and verify that it produces the correct outputs. We can't always make sure our program works under every single condition, but we should have some basic inputs and make sure that we understand that it generally works okay. So another way that this program can be run, if we look at the input 2, that is that same string that I just used. So if I run dna.py on with that as the input, you'll see that this program also works in a way that if you give it a file instead of a string, it will read that file for the contents and then use that as the input. So that's really convenient. It's a handy little shortcut that I often use in programs, and I'm going to teach you how to do that. So one of the most important reasons why, like I said, why we named this called DNA.py is so that I can use a program called pytest. So I'm going to execute pytest here and see what happens. You see it says it finds tests DNA underscore test.py, finds that file, and then inside of it there were 5 items, 5 tests, and you see here each one of these ellipses is each one of the tests, and they all pass. So we got a passing grade of 100%. You're going to be using this testing as you write your versions of this program without looking at the solutions, and to see if you can come up with clever and interesting ways to solve the programs. So we're going to be going over pytest much more, but that's how we're going to get started. So for you to get started, first thing to do is to rm test the DNA.py, and you should have installed a program called new.py. It is one of the dependencies that was just installed at the beginning, and so with that we're going to create a new program. And how does new.py work? Well, let's run it with -h and see the documentation. You see it's picking up some defaults here in a file that I've written in my home directory called new.py. new.py in my home directory. This is a bit of defaults here, but I've defined my name and my email. So if you look through the program, you'll find that this is something that you can do. So that's why it's coming up with my name and email. So when I say I run new.py with -h, it says that the program name is a positional argument, and it is a required argument. So you see that these other arguments here have brackets around them. The brackets mean that these are optional arguments, and the -n, -e in front of these, those are the flags that precede the argument, so that they're essentially named arguments, whereas the positional argument is just falls at the end. And you can have one positional argument, 2 positional arguments, and their position relative to each other defines what their meaning is. That is, as opposed to these flags, which can be given in any order. You could put -e first, and then -n, and then -p. It doesn't matter. So these are the arguments to our program, and here I show you how to run this to create a new program called DNA.py with the purpose of tetranucleotide frequency. So if I run that, copy that, paste it, I now have a new script called DNA.py. And the reason for this is that it's very difficult to start from a blank page. I know this as a writer, I know this as a teacher teaching new students, and so I wrote this for my students, and I actually use it every single day of my work career to start new programs, because I don't want to have to remember how to write argparse arguments, and I just have a structure that I've come to rely on over the years, and I find it much easier to have Python write the beginnings of a Python program for me, so that they're always well formatted and they work right off the bat. So if I execute my new DNA.py, you see that it produces documentation. I run it with -h, it produces the longer documentation. I have several examples of how to take a positional argument, a named string argument, a named integer argument, a readable file, and a Boolean flag. I have all these examples there for me, so all I need to do is modify the program and go from there. I find it's much faster for me to get going this way. So that's what we're seeing here, and we want the program to produce this as the output instead of what it's currently doing. It's producing all of this. The goal is to take this boilerplate and turn it into something that's more focused on what we want our program to do. So you see here that it should take as a positional argument a single argument that we wanted to print DNA here so that it indicates to our user that this is an input DNA sequence. And you see that there are no other positional arguments and there are no other options except for the -h and --help. So -h is what's called a short flag. Traditionally in Unix, it's a single dash followed by a single character, and the long option is traditionally 2 dashes followed by a longer, more meaningful word. Not every command line program works like this. Sometimes the long names are preceded with just 1 dash. So it depends on the language and on how the author wrote it, but this is generally how Unix command line programs are expected to work. And the other big thing here is that notice here, if we run our program with 2 positional arguments, that our program will not work because it says it doesn't know what to do with the second one, ggtt. So that is what we are looking to create. So going forward, let's talk about how to use argparse, and let's just talk about the structure of the program that we have here. The first thing that you'll notice is at the top there's this thing called a shebang. So it's very common to call the exclamation part a bang, and so I don't know why, but the thing in front of it is maybe called the sh. So together that is the shebang, and this is a special kind of comment character. So in Unix command line programs like shell programs, the hash sign precedes a comment line. So normally any line starting with this would be ignored, but this is a special comment. It's followed by an exclamation point, and then it's telling the operating system to use the environment program to look for Python 3. And when we looked over here and we said which Python 3, that's looking in our environment, and we actually have a virtual environment right now. So it's going to find the Python 3 that's running in our virtual environment. So that's what's happening when we do /DNA. It's finding this Python 3, and then it's using that to execute the rest of the program. This is a string. Technically in Python, that's all this is, but it's a special string because it occurs right at the top of the program. This is a doc string. And because it occurs at the top of the program, it's a doc string for the entire program. And if we look at ours that was created, this doc string is a little longer than one that was created by new.py. It has some additional information about who wrote the program, me, and the date on which I wrote it, and what the purpose of this was. And that's important to me because if someone else encounters my code and I leave it behind, I would like for them to be able to contact me and to ask me questions about the code. So I always put my name and email address in my programs in case someone needs to ask me questions. You see here I'm importing argparse. Now this version over here, I'm going to make, this is what I start off by explaining that in my book Tiny Python Projects, I created a version of this that does not use type hints. So this is the version of the program that would be created by that. So I'm going to first, I'm going to copy DNA to dna.orig, and then I'm going to open up DNA, and I'm going to make this one look like that. So I'm going to get rid of this typing information that we're going to talk about in a little bit. That's some typing information. We don't need that. And I'm going to go down here. I think that's pretty much it. Oh, nope. Right here, I'm just going to return what comes back from parser args. And we're going to talk about these bits here. But first, I just want to introduce you to importing argparse. This is a statement that tells Python to go find the module called argparse, which is a standard module. It's always installed with Python, so that wasn't part of our dependencies. We're going to use argparse to parse our arguments. And in order to use it, we have to import it first. And then the next thing we see here is a function. So the functions are defined with the def keyword, and I always put get args first, so that as I'm reading the code, I will see what the arguments are to my program before I have to get into the rest of it. And inside of get args, there is, the first thing you see here is another docstring. This is the docstring for this function. It's good form to always create a docstring for your functions. And then from there, we create I want to make my program look like this, so I'm going to change this positional argument to be called DNA, because that's the thing that we're taking. The metavar, I'm going to put in all uppercase DNA, because that was the thing that we saw on the command line when we ran it. If we look up here, it's right here, this DNA, that's the metavar. And it just helps the user to understand what we're trying to ask them for. And so I'm defining a positional argument, and the reason why it's positional is because it has no single or double dash in front of the name itself of the argument. Whereas all these other ones have a single dash and then a double dash for the short and long flags. Since I don't need the rest of these, I'm going to just get rid of them. And I'm changing the help to input DNA sequence. So with that, the other things here, I'm just going to print the arguments. And let's see what we get. So this is the program that I'm encouraging you to write so that we can just get an understanding of how this works. So let's look at point number 6 here. This is the parser object that's going to be created. And this is really the core of why I wrote this program. I don't want to commit this to memory. So I just like to have my program write that it creates an argument parser. This is the description of the program that it will print. And I always like to use the defaults help formatter, so that shows the default arguments if I choose to define them. So looking forward, number 9 here. All my programs will start in a function called main, and there's a long reason for that. If you have any background in C or C++, I work a lot in a programming language called Rust. Those programs they must start in a function called main. It's not a requirement of Python. You can start in any function you want. You don't have to define functions at all. You can just start writing code right at the top of the top level of the program. But this is a better way to write Python. There are some issues with Python, especially with scoping of variables. And so I find it much, much nicer to always put my code inside of functions, always have a main function, and then there's always this couplet. Another reason why I wrote this program is because I don't want to have to commit this to memory. There's always this couplet at the end that looks at the current namespace. So these are there are many double under special variables inside of Python scripts. They're called dunder variables for double under. Dunder name is the namespace that we're running, and so when we use this program when we use this piece of code as a program, the namespace will be double underscore main. But we can also use this file of code as a module, and when we import it into another script, the namespace will not be main. So this is determining if we're running this as a program. It's a hack. It's a dirty hack that I really don't like about Python, but this is the way it's done. And again, I don't want to commit that to memory, so that is why this couplet is put there for us. It must always be the last 2 lines of a Python program. And essentially what happens is Python reads the entire script all the way down, defines the get args, defines the main, and then when it gets to the bottom it says, now go run main. And so now our program comes here to main. You see it takes no arguments, there's none given in the parentheses, and so the first thing it does is call get args. Get args goes up here, executes this. It takes no arguments because none are passed in through the parentheses. It creates a parser argument. At runtime, it adds a DNA argument, and then it will parse those arguments and return that from this script back to main, and then we're going to print it. So with that, I'm going to open up a second terminal. I'm going to go into bioinformatics Python 01, and I'm going to make sure I save this program. And now when I execute DNA-H, you see it shows the output that we want. There's a single command line argument, and if I run it with AACC, you'll see that it prints this thing called a namespace. So we've already talked about namespace. This talks about the namespace of the program. Now, unfortunately, this thing is talking about a namespace too. So the thing that's returned by get args is returned from this parse args. That object is a namespace object, and it has inside of it something called DNA, and it has the value that we passed. So that's handy. It's very, very useful. Argparse is an incredibly useful program module that you should definitely learn to master. There are some problems though with this that I think that can be improved upon, and the biggest thing is that this namespace argument is dynamically generated when the program runs. So there's two here in this little note. I note that there's an element of compiling a program into machine code and then executing it. And in some languages like C or Rust, the compilation is done separately. It has to be done first, and then the program is run separately. The compile program. Python is just text, and it goes through a compilation program, but it goes compile straight to run. And there are errors that can be detected at compile time, like if I remove this parenthesis, now this is just not valid Python. So if I try to run this, it never even gets through the compilation part, because this says here that it was never closed. And there are tools that we can use to help us find those. Let's see, sometimes I use something called TY. Let's see if TY is installed. So I'm going to, let's see, the first thing, so since I have opened up a new terminal here, the first thing I need to do is I'm going to go to the root directory here. I'm going to source v bin activate, and I'm going to do a uv pip install for TY. Very useful program. I'll probably add it to the dependencies here, and maybe that will be installed for you. So if I go back in here and I say ty check my DNA program, ty is a program that can find errors like this. So it's saying that it's getting confused here. It doesn't understand. Well, first off, it wants to see an else here, but well, actually, surprisingly, it's not finding the problem with with that. Let's put this back here and see what TY says. Okay, actually, it was just getting confused. So it was not able to parse our program. It was telling us that there were problems, but unfortunately, it didn't tell us the right one. So there are some issues with how loosely Python can be interpreted, and I'm going to try to show you some tools that will help you write Python better. One of the things, let me show you something that you could do that's a pretty terrible thing to do. Instead of printing args, let's print args.dna, and let's see how that works. Let's go, we're going to run our DNA program with AACCGGTT. And you see it prints it. That's cool, because I told it, instead of printing all of args, I said print args.dna. So just print the DNA thing inside of it. What would happen if I said print that divided by 2? What does it mean to divide a string by 2? For a moment, I'm just going to, I have P3 as an alias on my machine for Python 3. And if I just run Python 3, it gives me an interpreter here. And let's just create this string. It's a string, so I put it in single or double quotes, it doesn't matter. And if I divide that by 2, I'm going to get this exception that happens, because that's really not something that you can do. You can divide 4 by 2, and it will give you 2, and that's fine. But it doesn't make sense to divide a string by 2. So what happens if I try to run this program with that input? It blows up. It's the exact same thing that we see in the the console here in the REPL. REPL is REPL, read, evaluate, print loop. We see here the exact same error occurs. And the question is, we know that DNA is a string, and we know that we're trying to do this numeric operation on it. Shouldn't that be an error that is caught before runtime? So you see here that the program runs, it compiles. It's not the same as if I go back and remove that and try to run the program. It never even gets to the point of executing that, because it says, hey, I can't even compile this into Python. Well, in the same way, couldn't Python look ahead and say, well, you can't do that. I know that I won't be able to do that. But that's not the way Python works. This is a runtime error, and I would like to push this into being a compile time error so that I can find these kinds of problems well before execution. So there are a few tools here that I recommended at the time I wrote this book, and they are kind of mostly out of date. There are better programs. Let's see what TY says. Let's have TY check our program here, and you see TY passes, so that doesn't find any problems. There's something called pylint that is a linter that will find a lot of common errors, and we see here it finds no problems. It gives me a 10 of 10. Well, fantastic. There was for a while something called mypy that did a pretty decent job of doing some type checking. So types are like, is this thing a string? Is it an integer? And there for a while I was using mypy and getting some useful output, but that tool doesn't seem to be as strong as it used to be, or maybe that there are better tools. So we're really finding, and I'm show here that at the time when I wrote this book, when I ran mypy, it didn't find any problems with this source code. So what can we do? How can we get around this? So I'm going to take a little detour here and get into some business here about types. And in order to get there, I'm going to have to start with this little excursion into something called named tuples. So let's talk about what tuples are. Finally, mypy came back here. It was very, very slow. So not something I enjoy using. All right, so I'm going to go back into a REPL here, and I highly encourage you to get used to using a REPL. It's a great way it's one of the best things about Python. It's a great way to verify that you understand how a bit of code works. So let's talk a bit about like a list. So in Python, we create lists by using square brackets. So I'm going to create a list here called seqs, like it might have some sequences in it, and it's an empty list here. The other way I could do this is to use the list function, and in either case, if I run type on seqs, it tells me that this thing is a list. That's cool. So if I say seqs.append and I put in ACT, and with strings in Python, it doesn't matter if you use double or single quotes, and I look at seqs now, seqs has been altered. It now has, I have appended ACT to that. There's another function I can use called extend, where I can add several items to the list. And if I look at seqs again, now it has 3 elements, and they are in the order that we added them. Extremely handy. I can print the seqs, which is essentially what's happening when I just evaluate them. It is a data structure, and so Python turns that into the string representation of a data structure, and it puts square brackets around it. And one of the other crucial things here is that I can change an element. So I can talk about seqs at 0, and that is ACT. Well, if I want to change it to TCA, and I look at seqs at 0, now it's TCA. And if I look at seqs, you see it's TCA. And so that's useful. That can be handy. Sometimes you would like to be able to, often you want to be able to change a list, but sometimes you don't. So there's another way to create something that's like a list, but it's called a tuple. Now, so one of the things about Python is I can just reuse the same variable name. So I'm using seeks again, but notice this time there are not square brackets around these elements. If I look at seeks, it this time when it prints it out, over here, this you saw that this was it had square brackets around it, but now it has parentheses around it. And if I look at the type of seeks, it is a tuple, which is like a list, but there's some crucial differences. It would be very common to write this out also with parentheses around it. But really just putting commas in between elements creates a tuple. So one of the most crucial parts is that it is immutable. So if I try to append something to this, seeks is not modified. So once you create it, it's permanent. I can't change, I can't add to it, I cannot change an element inside of it, and that's useful. It's one of the few immutable data structures in Python. Strings are also immutable. And that can be, you can use that to your advantage in programs. For instance, I want to use this to represent the arguments to my program because those are essentially sacrosanct. They should not be changed. Other elements in my program can be changed, but the data that's coming in, the configuration from the user, I pretty much never modify that. And one way I can do that is by putting the data into a tuple and passing that around. So let's talk about the idea of creating a tuple that represents a sequence object. Here it has a sequence ID and it has a sequence associated to it. Let's just pretend we've got this. And what's cool is I can talk about the first element of it and the second element of it. Of course, we're starting zero-based offset here. So 0 is the first element and 1 is the second element. And tuples can get confusing, and it can be confusing to remember that you're 0 offset. And it would be nice to create to have a data structure where you talk about the ID and the sequence instead of the position 0 and 1. And for that, we have from the collections module something called a named tuple. Okay, what is a named tuple? Well, it's this awkward bit of syntax that you would have to remember that to create a named tuple, you're importing this function called named tuple, and you pass it two arguments, a string representing the class name for the object that will be created, and then the names of the fields for those classes. So I'm going to create this thing called a sequence. That's going to be this sequence object, and if I say what is the type of sequence, it is itself a type. So I have created a new type, which is something you can do in Python. It's kind of cool. In a sense, this might be called a factory in some ways of thinking about it, because it's a function that's used to generate new objects of the sequence class. And it's very important. Convention says that we use title case for these kinds of types. So now I'm going to create this seek1 using my factory. So it has the ID and it has the string here. And if I say what is the type of seek1, it is a sequence type. Very cool. And I can now, I can also create a second sequence. Let's do that. Whoops. And so if I say what is seek1, it has this nice string representation that it prints out, and type 2. And you see here it has ID is equal to this, seek equals that. It's very, very useful. So with that, I can also use these. So it is still underneath a tuple. So I could say, for instance, create a string by concatenating this string to the thing in seek 0, and it creates this new string here that has the ID. But the whole point of this is that I'd like to be able to say seek ID, which is very handy. And I could say this other one, this other string, I could say sequence is equal to, and I can say plus seek. I'm going to use seek2, seek. Very cool. That's nice. It's kind of a lot for me to remember. So I would like some easier ways to create this. Oh, the other crucial thing here is that, like, if I say seek ID is equal to XXX, I'm not allowed to do that. Because underneath this is still a tuple. It is still immutable. So how do we add types to named tuples? Well, we can actually do that by importing from the typing module this thing called a named tuple. And I'm not going to type all this into the REPL. We're just going to use the book here. So from this typing module, there's something called named tuple, and I can create something called a class. Now, I am not a fan of object-oriented programming. Python is itself an object-oriented language, and everything that we're using is pretty much is an object, and that's fine. I just don't tend to write objects myself. That said, I am creating a class here which is used to instantiate an object, and that's about as much as I'm going to go into for objects. I'm saying that there's a class that has the name sequence, and it derives from a base class called named tuple. And that's one of the essential elements of object-oriented programming, is that you can have base classes, and a derived class can inherit all of the elements of the base class. So because we're using named tuple as our base class, we're getting all the goodness that we just talked about. That underneath the data structure here, it's just a tuple. There's something in the first slot, there's something in the second slot, and there are names associated with those slots. But there's something further I can do here, is that I can add this type hint. Now, there are a lot of Python programmers, and some are good friends of mine, who hate the idea of type hints, and they would never want to do this. So take this with a grain of salt. I like using this kind of a data structure with type hints. Your mileage may vary. You don't have to do this, but I find that it helps me to write programs that are more accurate and easier to check. So I think I will go ahead and show you a couple problems with this. I'm going to import this. I'm going to create this class called a named tuple, and I'm going to say it has an ID that's a string. It's going to have a seek that's a string, and then I'm going to hit enter a couple more times, and now I have defined this. So now if I say what is the type of sequence, I have overwritten the previous definition, but it's still a type that I've created, and I can still use the same kind of syntax here to create a new sequence 3. And it works exactly the same as before. Like if I want to print out the two elements of it, it prints it out like that. So since I have defined that these fields have string types, it might be nice, you might think it would be cool if when I try to define sequence 4 with a floating point value for the sequence, that this would in some way blow up and prevent us from doing anything. But you see that it doesn't. If I look at seek4, you see that it has a float. If I say what is the type of seek4.seek, the type of that, it is a float. So Python completely ignores the type hints. And that's annoying to me, but these are just type hints. And if you decide to put something else into that slot that's not a string, Python is not going to stop you. So how does this help us? Well, we're going to have to use some other tools to help us find these kinds of problems. But what this does is that it allows us to statically define the data structure with type information. And so I'm going to go back now and go back to my program that I wrote and show you how we can, let's go back here to, I'm going to get rid of that DNA version, and I'm going to move the DNA.orig back to DNA.py, and let's go back and look at how our program, the one that was created by new.py, how it differs from the one that we were just writing. You see that here I'm importing a couple elements from the typing module. There's my name tuple that I'm using as the base class for a class that I'm creating called Args. Derives from a name tuple. It has these 5 slots in it. They hold string, int, a text IO, which is a way of representing a file handle, and this one, this 5th element, it holds a Boolean, which is a true or false value. So I want to change this. My positional argument is going to be called DNA, and I don't need the rest of these arguments. Because I'm not going to be using text IO, I'm going to get rid of that. I'm going to go down here and change this to DNA, and I changed my metavar to DNA, and I called this input DNA sequence. And then I don't need the rest of these arguments. And one of the things that changes here is that now I capture my parse args into args, and if you remember, that's this thing called a namespace. It was this dynamically generated argument that we have, this value, and instead I want to install args. Instead of returning that, I want to return args where DNA is equal to args.dna. And let's go back down here, change our program back to printing args.dna, and let's see how our program works now. So DNA, and I say AACC, and it prints it. If I try to divide by 2, it still blows up, as would expect. But now if I say check DNA, we see that we're getting some TY is able to see, hey, args.dna has the type of string, and this has the type of a literal 2, and it says this is an unsupported operator. You can't divide a string by this 2. And so that's useful. And that's not something you get when you're using the dynamically generated namespace argument that TY is not able to figure out that that's a string, even though it clearly is a string. I've not done anything to change the value from a string to something else. So that is a long explanation for why Args, new.py, adds this class to represent the arguments and adds this type information is because it will help us to find problems like this. So if you don't want to use this and you don't want to go down this road, that's fine. You don't have to write your programs like this. But as you write longer and longer programs, you may find that tools like this will help you find errors. So with that, we're going to move to the next part, which is reading input from the command line or from a file.
Okay, so we're going to pick back up with reading input from the command line or a file. And so the first thing that we need to do is to get our program back to working. So we're going to get rid of that silly division. And we can just run our program just to make sure. Let's call it DNA and AACC2G. And it works. So there is a case where sometimes I would like to give it the name of a file because it can be cumbersome to print, to paste a large amount of sequence data on the command line. Sometimes we get huge files, and even in testing with Rosalind, I would get something like 1,000 base pairs long that I need to count. So I would like to add a little option into the getArgs function that detects when the DNA that's provided to us is actually a file name, and instead open that up. It's pretty straightforward. Let me show you how to do that. So here in getArgs, what I'm going to first do is I'm going to right after I parse the args, I'm going to test if if the args.dna is a file, and I can do that with a function in the OS module. OS is for operating system, and inside there is a path module, and inside there is a function called isFile. So I can say if it's true that args.dna is a file, then I want to open args.dna. That's going to give me a file handle. And I can open that file and call read on the file handle, and I can additionally strip off the new line at the end, and I can overwrite args.dna with the contents of that file. So let's just talk about that for just a moment. If we look at this again here in the tree of our this directory, there is a file in here called tests. Under tests, let's cat this file. Tests, inputs, input. Let's take input 2. That's fairly long. Let's take input 3. I think that's the longest. That was one of the strings that was given to me on the Rosalind site. And let's just open up a terminal real quick, and I'll call this. I'll call it DNA. I'll set it to that string. And I'm going to, in order to just walk through this code with you, I'm going to have to import the OS module. And I also, over here in my script, I'm going to need to make sure I'm doing the same up here. So I have not imported OS because I don't normally need that. And so I'm importing OS, and I can call help OS. Very handy. And one of my favorite things about the REPL is that I can read documentation here, and I can search in here for instance, the path module or the word path, and I can find everywhere where path is talked about. I'm going to hit Q to quit that, and I can additionally look at the help for just the os.path module. And I can see here it has lots of very useful functions, like giving me the base name and the dir name for a path. I have whether something exists, and now that could either exist as a text file, as a file, or as a directory. And then there are specific tests for, is this a directory, is this a file, is this a link? So it's a very handy module to be aware of. So let's ask about specifically help os.is file, and it tests whether a path is a regular file. Now it isn't explicit here about what the return type of it is, but it is a Boolean function. So it returns a true or a false value. So we can ask, let's get rid of the help here, and I can say, is this a file, my DNA? Yes, it's true. Fantastic. So I'm going to create a file handle variable. I often call this fh. And so I'm going to open that file. Whoops, it goes like this, open DNA. So DNA is actually a file name now, so it's actually a terrible variable name, but we're pretending like this is what we have over here in the program, where we're given something that we think is DNA, but now we've found that it's a file. And if I open that file, I have this file handle, and I look at the type of fh, and I see that it's this text IO wrapper, so it's this thing that I can use to read data off the disk. And I can actually call help directly on a variable, and it will give me the help on the type of the variable, which is just really handy. So with that, I know that I have opened this file. I can call fhread on the file, and it returns the contents of the file. Now notice that there is a new line at the end. That's very common, but it's not always the case. I don't want the new line. In this case, it won't hurt because I'm simply counting the A's, T's, and G's, so it doesn't matter if that's there, but often I don't want it. Let me point out something here. If I try to read the file handle again, I get nothing. So it has been exhausted. It has gone to the end of the file, and it has to be reset or reopened in order to read the file again. So let me do that. Actually, one of the things I can do here is I can call open and then directly call read after it. And I can do that as many times as I like because it's opening the file new every time. Now, something to be aware of is that this has to be read into memory. And if you're dealing with a 10 gigabyte, 30 gigabyte human genome file, that's a really bad idea. You probably don't have 30 gigabytes on your personal machine, or maybe even on your server. So it's a very bad idea to call read like this on an entire file unless you're reasonably sure that it can fit into memory. There are far better ways of reading a file in genomics. So with that, I can just keep tagging on other string functions. So what is the type of the return from read? That is a string. So there is in the string class a function called rstrip. And if you're not familiar with that, we can do help string, and it will tell me all the things that I can do with string functions. So very handy to know. So if I call open read rstrip, I get back the contents of the file without a new line at the end. So that's exactly what I'm doing. I'm opening DNA, read strip, and then reassigning that to args.dna, and now args.dna is actually a string, and it is not a file handle. So if I run my program now with AACCGGDT, works, and if I run it with tests, inputs, input 3, let's see, there we go, it works. I had failed to save the file before I executed it. So that is how to read the input into a string. So let's talk for a moment about testing your program and the tests that I provided for you. We know that if we give it a string like ACGT, that it should print out 1, 1, 1, 1. And so how do we go about testing our program to make sure it does that? Well, I have written for you under the tests directory, and if we look at tree again, under the test directory, we see there is a file called dnatest.py and the various input files that we've been using. So let's take a look real quick at test.dna. And writing test is really beyond the scope of this project. I have provided you a lot of tests that I hope that you will read and learn how to write your own tests. But mostly what I hope to accomplish by walking you through this material is to prove to you that tests are really useful to have, and maybe you will want to write them yourself. The structure of this file is a little different than what we saw with the function with the program that we're running. For one thing, you'll notice there's no shebang line up here at the top. There is a doc string. Very simple doc string to say that this is test for the dna.py program. But otherwise, this is not expected to actually execute as a program. It's going to be used by pytest. So pytest is going to read this straight down, and every time it finds a function that starts with test underscore, I believe it also looks for functions that end with underscore test, but I usually put test at the beginning. It's going to execute every function that begins with test underscore whatever. And it's going to run them in order. So I pretty much always write my tests in increasing level of difficulty to make sure that if something simple fails, then there's really no point in testing the more complex things. And when I wrote this for my students, always the first test is, have they created a program that is the program name that I expect? There many times the students thought that they could just create any program name at all. I'm like, nope, it has to be called dna.py in order for me to be able to find it. So up here at the top, I have set up a few variables that I will be using throughout the program. We've imported the OS, which you've just seen. Platform is a module that will help me know if I'm on a Windows program or if I'm on a Windows operating system, or the default then would be, the assumption would be some sort of a Unix or a Linux platform. And then from the sub-process module, I'm importing a function that will allow me to call another script, which is something that's extremely important to do in bioinformatics. We're constantly using Python and other programs to stitch together other programs into some sort of a working pipeline to transform some input data into some knowledge. And so this is a very, very useful program a function to know how to use. Up at the top, I have defined a few variables, and it's very common in languages that allow you to establish constant values to put those constant values, the names of them, in all uppercase letters. Python does not allow for constant values. It is possible to overwrite the values of these, even though like test1 here you see it is technically a tuple because it has been surrounded by parentheses and the values have been separated by commas. I'm not able to change one of the values inside of it, but I am able to overwrite test1 entirely with some new value. I don't want to do that, but I'm just telling you it's not possible in Python to prevent to be able to say with like a constant keyword here at the beginning that this should never change for the life of the program, that you can do in other languages. But these all uppercase variables do let me know that these are supposed to be constants and I should leave them alone. So my first function is test exists. I have annotated this with some type information. So because there's nothing in the opening and closing parentheses here after the definition of the function name, that lets me know that there are this function takes no arguments. And this arrow lets me know that this returns the type none. I have a doc string here that just said testing that the program exists. And here we're using the OS path module again, which we just saw. And now I'm just using the function called exists. And like I said, it only tests that something exists. It could be an empty file, it could be a directory, it could be a link. So it's not a perfect test, but to get started, we just want to make sure that something called dna.py in the current directory exists. Now, something that's kind of funny is that this is in a subdirectory called tests, and yet the path that I'm looking for is in the current directory. That's what the // means. And so this doesn't work if you execute it in the test directory. It's meant to be executed actually in the base directory by calling pytest. So if I call pytest here, and I think I'm not sure if I'm still in my virtual environment. So there we go. It has called pytest, and it has, and I've called pytest from the main directory, and it went through and it found this test.dna in the subdirectory, and it executed it from this current directory. So that's why it works. So the first 3 tests pass. Actually, we haven't even done much with this program, and yet it's already passing a few tests, but it is failing on when given a string of 1A, 2 C's, 3, it's not printing out 1, 2, 3, 4, it is actually printing out just the sequence. And so what we see here from the failing test is that this assertion right here failed. The output from the program does not equal the expected. So let's keep looking at our tests and understand what passed. So the program exists. That's great. Then it went to, and we can get more information from pytest by calling with the v. And let's just take a moment to look at -h. If we run pytest with -h, it gives us quite a bit of documentation about how to run it. There's so much that you can learn here about pytest. I really recommend digging deep into this. One of the most important, the 2 most important flags for me are -v for verbose and -x, which tells it to stop on the first failing test. So it tells me here exists, usage, and dies no arg all pass, but then it failed on test arg, and then it just stopped. Because there's really no point in keeping going. So how did I test for the usage? Well, for the arguments -h and -help, I run this command. So I'm using an F string here where I'm putting run dna.py with this argument -h and then this argument -help, and then I get back from that a tuple of the return value, which I always abbreviate RV, and then the output from the program. And the output will include both standard out and standard error. And so I look at the return value and I assert that it is equal to 0. Now, what is assert? If you come from any background in like C or C++, you might be aware of there's a similar function there. If I assert a true value, then everything is great. For instance, I can say 2 plus 3 is equal to 5, and that is true. If I were to say that was equal to 6, then I would get an assertion error. So 2 plus 3, if I look at that, that is a false statement. So if I were to assert the actual value false, then I would get an assertion error. If I were to assert, actually, this is a kind of a dirty little secret, if I were to assert a value 1, it works, and if I assert a value 0, then it fails. And really underneath, Python doesn't have a true Boolean type. It uses essentially 1 and 0 to come up with what I like to call a truthy value. So therefore, if you assert something, there are other things that are truthy and falsy. The empty string is actually false, so any non-empty string, even if it's a blank, is actually a true value. Same with an empty list is falsy, but if there is any value inside of it, even a false value, then that's true. So I can put false in here, and because the list itself is not empty, then that is a true value. If I do the same with a set or a dictionary, then those will also be, if they are empty, then they are false. So that's what assert is doing. As long as what comes after assert is true, then assert succeeds. If you give it something that is false, then the assertion raises an exception. You see here, this is the exception, an assertion error, and with that the program dies. And because I told it to. If I were to go back to run pytest without the -x flag, it would test arg would fail with an assertion failure, but then because the exception is caught and printed out like this, it will move on to the next test if I want it to. Under normal circumstances in your Python code, if you raise an exception, the program will just stop right there and provide you a traceback. So the assertion that I'm making here is that the output, when I lowercase it, it starts with the word usage. And if we go back and let's just look at this, dna.py, if I run it with -h, you do see, in fact, the first word is usage. And so this is just a typical behavior of Unix command line programs. We call this the usage because almost all of them print out the very first word, usage, and it tells you how to use the program. So usage passes because we are using argparse. Argparse, by the way, if we go back and look at our program, we have never defined -h and --help, so that is done automatically for us by argparse. And in fact, if you try to use those flags, it will conflict with argparse and it will complain. So don't do that. So we get a lot of good stuff for free when we use argparse. So the usage fails. The usage passes here, and then test dies no args. So what happens when we run our program with no arguments? Because we have defined this with argparse to say that there is a single required positional argument, and positional arguments are by default required. Just by virtue of using argparse for this, if the user tries to run our program without an input, then it raises an exception. And so when we run get status output with the program all by itself, the return value is not equal to 0. So here I'm asserting that the program runs correctly with -h and it just simply prints out usage. Here what I'm saying is assert that the return value is not 0 when I run it with no arguments. I'm asserting that it dies. And you'll see this in my test names. When I'm trying to ensure that the program correctly fails, then I put into the name of the function dies. So it dies, it does not return a 0. 0 means 0 errors for the return value. So 0 is a good thing. And if it's not, we want to make sure it's not equal to 0, and then we want to make sure that the output starts with usage, which indeed it does. So just because we have a well-structured program that uses argparse, we get a lot of really good stuff. We get a couple tests almost for free there. And what's happening here is on test arg that is failing. If I go back and look at that, pytest -xv or vx, it doesn't matter which order. We see that when we are passing it, we're expecting we're expecting 1, 2, 3, 4. That's the expected value, and the output is actually this string. And so what's going on here? I'm iterating over the values of test 1, test 2, test 3, and let's just jump up here and look at what those look like. Test 1, each one of them is a tuple that has a file name and then the expected output for that file name. So what's happening under test arg is I'm iterating over those 3 values. I'm unpacking the tuples into file and expected. For the first way to use this, I'm going to open and read that file, the DNA file. And then, here's an example where I didn't abbreviate that RV. So I call this retval and out. I run the program with the contents of the file, with the actual DNA string. I assert that that's equal to 0, and then I assert that the output is equal to the expected output. This is incredibly important when you write tests that you give it known input and test that it creates the right output. That might seem obvious, but I've actually had to argue with people that just running the program and seeing it like not blow up they thought that was a sufficient test. And I'm like, no, you haven't tested that it actually works. So, and then in the file version, instead, you see, I don't have the open read here. I'm essentially doing the exact same thing, but now I'm running it with the file name. So I'm asserting that this is my way of testing that when given a file, the program itself will open and read the file and then also still produce the expected output. So a rather straightforward set of tests that we're using here to check our program. And I really encourage you to read all of the tests that have been provided with the example programs that you're going to write. You can learn a lot from them. But this is how we're ensuring that our program runs correctly. Let's see if there's anything else I wanted to talk about here. That is an overview of the tests. One thing I'd like to point out here about using these tests is that there's kind of a couple different ways of writing tests, and here in the book I call it inside out and outside in. But really they're called unit tests and integration tests. Unit tests that's what I kind of consider them inside out. So a unit test tests an individual function. And so we've seen some functions here, but we haven't written a test for them yet. What I've showed you is what's called an integration test, because what I'm doing with tests, DNA, is I'm running the whole program. I'm running the DNA program from the command line just the way the user will do it, and I'm ensuring that it runs it the way that you would expect. So I'm not testing an individual piece of the program. I am in a way I am, because I'm ensuring, by instance, passing the file name, that it does know how to open the file and read the contents. But really I'm testing it in the context of the whole program hangs together, works as I expect, produces the return value that I expect, and I'm doing that from the outside the program using an integration test. Later I will show you here in this chapter how to write a unit test for an individual function. So that's what's all going on here. So let's get into the meat of the program now. What we have to do to make this program pass the test is actually count the characters in the input string and tell us and report the number of A's, C's, G's, and T's. So let's talk about some fascinating things about Python types. one of the first things that I think is just really useful to do, and I really encourage you to open up a REPL environment somewhere and follow along with me. Let us create a DNA, and let's set it equal to ACGT. And then let's talk about what is the type of this. It is a string. So what can we do with strings? Lots of things. If we help on string, or we can help on DNA, they both, actually interesting. Sometimes it works. Help on string. These are all the functions that I can do with strings, and we're going to be using several of these functions. That's really cool. One of the things, the first thing I'd like to do is to show you how to go over each one of the characters in a string. And we can do that actually with a for loop. This is a little surprising. Normally for loops are, you would probably be introduced to them in the context of a list. Like in a couple videos ago, I showed you a list of sequences that I created. Well, I can actually create a for loop for base. I'm going to call it base in DNA. Now let me talk for just a second about this variable. You will sometimes often see for I in, like, say, range 4, print I. And you will see something like that, and it does work. And the reason for using I in this particular context is that it is an integer, and when you are going over a bunch of integer values, it's extremely common in code that you will read that people will use I for that placeholder. It is in fact a terrible variable name, and you should never use I pretty much in any other context. But a lot of times beginners will see that kind of code and they think, oh, a for loop, you can just call the value of the thing in the for loop, you can just call that I, and that's or X or in. Those are terrible variable names, and you should only use those if they're maybe specifically numbers, and only if it's a very small short for loop and you won't forget what the variable I stands for. It's much better to use a variable name that describes the data that you're dealing with, so that when you're reading this, it reads like English text, then a person can read it and understand it. And probably that person is going to be you in several weeks or months, and you will have completely forgotten how this code works. And so you will appreciate giving your variables good names. So for base in DNA, I want to print base. And it in fact works, A, C, G, and T. There's a number of things to note here. I didn't have to do anything special over DNA. It is just simply an iterable. So in the way that a list is an ordered sequence of values, you could sort of think of a string as an ordered sequence of characters. So another, I point out here, you might see for char in this print char. That would be another decent variable name to use, because you're specifically going over each character in this string. One thing I would notice, it would be terrible to abbreviate this as for CHR in DNA. This would actually work, but there is in fact a function called char, and it has as its the ordinal value here the C. I'm getting the ordinal value of C, and so under normal circumstances, if I were to ask for the char of that, this would work. But I have now shadowed the char function with DNA, with this. I have now made it into a string, and so it no longer works. So I have to restart my REPL here so I can show you that's what it would normally give you. Python does not prevent you from overriding, from shadowing some of its built-in functions like dict, list, char, ord. So you do need to be aware of all these functions and built-in keywords so that you don't end up breaking your program by accident. So Just a little side note there. So I want to count the nucleotides, and that means that I'm going to have to come up with essentially a decision tree. When I see the letter A, I need to increment some sort of a variable somewhere that is the number of A's that I've seen. So here I'm showing in the book that on individual lines I can instantiate 4 different variables for the count of each one of the bases, and I can set them equal to 0. I can actually do this with this little shorthand syntax that Python allows by essentially creating a tuple of 4 values over here and unpacking it into a tuple of 4 variables. So I can do that here in my, let's see, copy and paste. And so now I have, for instance, count A has been defined in my REPL. I do have a note here about how to name variables. So there's lots of different styles. There is I think that this is a nice readable way of writing variable names, but it is not the only way. So in some languages like JavaScript or Haskell, and I work a lot in a language called Elm, this would be the way of writing count A. But in Python and Perl and several other languages, this is the conventional way that most programmers in that language would prefer to write those variable names. And in fact, there is a style guide for Python code, and it specifically says that function and variable names should be lowercase with words separated by underscores as necessary to improve readability. So when I'm working in Python, I stick with Python naming conventions. And it's very important that they be consistent. So you don't use this style some places and this style other places. It's very confusing to the next person who has to maintain your code. So adopt the Python style when you're working in Python. Okay, so for that, if I'm iterating over each base in DNA, I'm going to say if the base is equal to C, then the count of C is going to be set to whatever is the current count of C plus 1. So it's very important in my code that I first initialize these values to a count value of 0 so that when I try to do this will work. So for base in DNA, and you notice here I can indent 2, I can indent 4. When I'm writing code, I always indent 4. It doesn't matter for Python as long as it's consistent. So when I'm in the REPL, I'll often only indent 2. So I can say if base is equal to C, then count of C is equal to whatever it is currently greater by 1. Oops, I didn't define DNA because I had restarted my REPL. So let's go back for base, if base, there we go. And now I can see count of C has been set to 1. Now count of A is still 0, count of G is still 0, and so is count of T, because I didn't test for those other values. And so that is something that I will need to expand upon. One quick thing is that this is a very long way of writing this out. There's actually a shorthand way to do this using this plus equal operator. So an operator is this like symbol that comes between a left-hand side and a right-hand side, and we have lots and lots of operators like the plus sign. So 4 plus 6 equals 10. If I have a value like count of C, I can make it go up by saying plus equal, let's say 3. And so what is going on here is that on the left-hand side is what the count C currently is, and on the right-hand side is how much greater I'd like it to be, and plus equal essentially pushes that value over to the other one. And so now if I look at count of C, it's now 4. So it's much more common to see code that looks like this. For base, if base is A goes up by 1, C goes up by 1. It's a lot less typing, and so therefore your code is a lot less error prone. So let's talk for a second about this code. This is a simple decision tree that I've got using if and then elif is a way of writing else if. And so I'm testing if is base is equal to each one of these four conditions, and the other version, the other keyword that you can use in this kind of a tree is else. So that would be the default version for anything else. Because we don't really have an else, we're only specifically counting these four characters. So I only have these conditions. And if I were to type out all this code in the REPL and run it, then you can imagine that for this string, I would end up with counts of 1, 2, 3, and 4. And so that is how to write a little decision tree. I want to point out a couple of other things about print. You can change the separator. So when we print values like print hey and there, then it prints out hey there with a space in between. That is the normal way of the normal separator that print will use, but I can tell it to use a different separator of, like, say 2 colons, or I could say use a separator of the comma. And so that is something that's handy to know about print. And the other thing is that I can put something else at the end. For instance, if I don't want it to print a new line, I can can put the empty string there, and you see here it does not put a new line. Or I can print something else, like I had a background in high school of journalism, and so we always put -30- at the end of a story. So if I want to put that there, I can do that. So a couple handy things to know about print. Okay, so let's talk about writing that, the code that we've been playing around with in the REPL. Let's put that now into our version of our program, and let's see if we can pass a test now. So DNA is going to be given to us on the command line. I can say for base in Args, and you know what, this is I can type all this out, but it's actually solution 1. So I'm going to go down here, and I'm going to just grab this code. Since I'm showing you this code now, so since we've already gone over it, whoops, and so it shouldn't be any surprise to you. I would encourage you not to look at the solutions until you've had a go at writing the programs yourself. There are a number of challenges along the way where I say, here's what I expect for the next part to look like, and I encourage you to figure out how to do it yourself. So with this, let me run dna.py, and I see it seems to do well. It seems to do what I expect. Let's just run it with, say, the empty string. What happens? It prints zeros. That's good. So it seems pretty good. Let's run pytest-xv and see how we go. Hey, passing all of our tests. There's something really satisfying about seeing that. To me, it's extremely motivating. So I hope you find it pleasant when you have all of your tests passing as well. So what is going on in the book? I have a lot of extra programs that that worked at the time, and they don't seem to work as well. And so I would actually encourage you to not use these test extensions. And it's a good point. It's a good time here to bring up. There is something called a make file in this directory. So if we look at tree again, I haven't talked about this file called make file. I have a whole appendix about how to write make files. They're very, very useful. But essentially what's going on here is that I've created a couple of targets. A target starts with a word, something that looks like a variable in Python, and it needs to be flush left, and it ends with a colon here. And after that recipe or that target is something that needs to be, some command that needs to be executed. And here you see this very complicated command that I was using originally, and pylint and especially MyPy don't really seem to do what I want anymore. And so I've simplified it down to running pytest, and this is another way of running pytest is by executing Python 3 and telling it to load -m, the module pytest. And then that runs pytest with -xv, and then the --flake8 option, which will run the flake8 linter on, and then it's going to, we're telling pytest to specifically look for any tests that are in the program dna.py, and I'm going to show you how to write tests in there, and then to also execute all the tests that are in the test file that we've looked at. And then this special all is a shortcut that I wrote for myself. It uses this shell script to test all the solutions that I've written. So that was a quick way for me to ensure that all the different variations that I presented all passed the tests, and without me having to do that manually. So I recommend that you read that as well. Shell scripting is a huge part of bioinformatics as well. So we've already taken care of installing the requirements. We're using UV for this now, or at least I am, and I encourage you to use that. This is showing you how to run this with the way that I was showing it at the time. I'm probably going to be updating the make files in the GitHub repository to have this simpler incantation. So what that is all goes to say is that I can say make test, and it's actually going to execute that for me. And you notice that it has thrown in a couple of extra tests. It threw in these ones called flake8. And so if I run flake8 on dna.py, you'll see here it comes up with no suggestions. Let's see. Let's create something that it might create a suggestion for. This would be bad, indenting at a different level. And let's see what flake8 says. Yes, it says the indentation is not a multiple of 4, and it's telling me it's on line 53, and sure enough, I can set number. I can see I'm on line 53, that it is not correct. So if I were to run this make test, you see that I get a failure here from flake8. That's useful. I feel like the more tools that you can use to check your code, whether that be linters or type checkers like TY. Let's see what TY has to say about this. TY doesn't actually see a problem with that indentation. It's checking something else. So you kind of have to triangulate on Python code because the compiler is so loose. Sorry, I had a little freak out there. I thought I wasn't recording. So that is what's going on with the make test, and this gets at something called test-driven development, where when you're writing code, I would encourage you to write tests along the way. You are using more what could be called a testing first cycle, because I've written all the tests that this should adhere to. But as you write your own code, I would encourage you to learn how to write tests as you're going along. This is a great quote: without requirements or design, programming is the art of adding bugs to an empty text file. So unless you can define what your program should do and what it means for the program to work, then you're really just kind of spinning your wheels. And writing tests will help you figure out what is a working program. So we could stop there. We have now learned how we've learned so much along the way, from argparse to how to iterate over a string, and how to handle tuples and write decision trees. Really an amazing amount of work already. But there's really a lot more to dig into if we're going to master Python. If we're really going to understand all the things that Python can do for us, it's really useful to just keep digging. What else? How else can I solve this problem? So the rest of these solutions are going to be showing you some more advanced ideas. So the first thing I'd like to show you is how to write a unit test. And for that, I'm going to create a function called count that's going to take as its input a string called DNA, and it's going to return as its output a tuple of integers, of 4 integer values. So what does that look like? So I'm actually going to go, this is solution 2, iter. And let's talk about this count function. So the first thing I'm going to do, I'm going to go over here and I'm going to change my code. I'm going to go back to DNA. And I'm going to put in here, I'm going to get rid of this. And I'm going to create this count function. Now, in order to bring this in, the first thing that I need to do is to bring in this tuple type. And I can do that by going up from typing. I'm importing named tuple, and I'm also going to import the tuple type. Whoops. Sorry about that. So down here in my count function, I've essentially moved all the code that we had in our main function. I've moved it into its own function. And I have the exact same code where I'm incrementing, I'm initializing 4 variables, going through my decision tree. But instead of just printing them, I'm now returning them. And this is a really crucial thing about writing tests, is that when I was just printing the output of the program, I had to run an integration test, capture the output, and then look at it and verify that it was correct. Now that I've moved this into a function and I'm not printing it, but I'm instead returning it, I can now write a function that calls this function and gets that value directly back, and then I can test it there. This is certainly overkill for such a simple program, but the point of this is to show you how to do these kinds of things. So now I've taken that, I put it into a function, and let's just make sure that we understand how to call this function and use the results. So it's going to give me, for instance, those counts are going to be returned by count of args.dna. And then let's just print those. And you see here, there's already a lot of things that you're probably looking at this code and saying, well, you could just print the count. So let's just go through this. Let's just play around with it. A, C, C, G, 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 D, 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 D. And it does work. And if I run pytest -xv, it passes. So this is another way to write this, but the whole point of writing this as a function was that I would like to write a unit test for that. So let's talk about what that would look like. So this is how to write one way of writing a unit test. Now, because I'm using pytest, inside of my code here, I'm going to create a function that's called def test_count. Remember, pytest is looking for functions that start or end with test. So I'm going to go over here, jump back to this code where I've already written it, so you don't have to sit there and watch me painfully type. I'm going to copy this, and it's my convention that I put the test for a function right after the function itself. It therefore serves as a test, but also as documentation. So I can see here, when I try to count the empty string, what I expect to get back is a tuple of 4 zeros. When I count this string that doesn't have any ACs and T's and G's, I expect to also get back 4 zeros. And then I go through and I say, well, if I'm only counting a string that has A, I expect to get back a tuple with a 1 in the first section, in the first position, and on down for C, G, and T. I expect it to look like this matrix right there. And then finally, I pass in something where I have a distinct value, a distinct number for each different base, so that I can ensure that I'm getting back all the bases correctly counted in the correct positions. So I have now written a pretty exhaustive and useful test of my function. And what happens is if I can run now pytest just on dna.py, then what happens is that it looks inside of there, and let's do xv, it finds the test count and it passes. And that's really, really cool. Let's just put in a test that we know will fail. So this is what a failing test looks like. It goes through all of these, and as soon as it encounters one assertion that fails, the whole test fails. So that is what a failing test looks like, and that's why these are useful. So now I'm showing here running it on the actual, just the program itself. It's not running the integration test. It's only at this point now looking for the unit tests. And I can do a bunch of clever things, like for instance, I can use the touch function in Bash to create an empty file. And if I try to count the empty file, it prints all zeros. Now, there's also a special file handle called dev null that is essentially an empty file handle, and it also returns zeros. Now, you may feel that that's not the way you want your program to work, that if it's given an empty file, it should actually complain to the user. Let's say that you're writing a pipeline that's analyzing a bunch of sequence files, and if you happen to come across a sequence file that has no contents or is not correctly formatted, that you actually want the whole program, the whole pipeline to stop. And that's your choice, and that's the way that you should write the program. It should die. It should create a return value that's not zero in order to indicate that something needs to be fixed. In this case, we're writing a program that doesn't care that we have an empty file. It's just going to print zeros. And so you have to know what the purpose of the program is in order to write it correctly. So now that we've done that, I'm showing here one way to print this out is I've gotten the count. It's giving me back this tuple, and I've got these values. Another way that I could print out the values, because I'm relying right now on the default behavior of print to put a space in between each one of the values, I could use a format string. So the way this works is I give it a string here. These curly braces inside are placeholders. There are 4 of them, and in the .format function of this string, so this is kind of a funny thing about Python, but this creates a string. A string is an object. An object has string objects have a format function, and you can read help string format if you want to learn more about that. And each one of these values, and I'm passing it format a tuple, each one of these values gets put into in order. Count A goes here, count C goes here. I think I might even have a little visual for that. The counts go into each one of the little placeholders, and that will also create, so if we save this, and the whole point of all of this, I need to go remove my failing test. The whole point of writing these tests is I can now start playing with my code, and I can ensure that whatever I've just added to my code, it still passes all the tests. And you see that all of them run from the very beginning to the end. And that, to me, is the proper way to test a program. You should always be running, well, sometimes you write very large programs and they have very long test suites, but for the most part, especially for these short programs, I think that you should run all the tests in order every single time you make a change. Here's another way to write that. So I'm showing you something here that I don't use often, but I think it's something important to know. Another way to write this is that I'm putting the return value of count. So remember, the return value of count is a tuple of 4 integers. And here I'm unpacking the 4 integers into 4 separate values. But I don't have to do that. It's returning a tuple that I could then put into counts. And it's very important that I call it counts and not count, because then I would have 2 values called count, and Python wouldn't do well with that. So I'm calling this counts, and then instead of printing each individual one like that, I can now splat this operator. That's one way of calling this star in the beginning is called splatting, and it will expand the tuple into the 4 values. I don't really like this, but I wanted to point it out to you so that you know, especially if you see this in someone else's code, you know what's going on there. So this will also work. How do we know it will also work? Because we save it and then we run our test. I can also run make test is another way to do that. So moving ahead, I can even shorten this up even more. I don't need to call that and put it into a value. I could actually do this. I can call count on args.dna and splat the return value of that. Let's see, maybe I missed a, I think I'm missing a parenthesis there. I'm running a code formatter real quick. Let's see. There we go. Let's see, I messed something up here with my code formatting. Sorry about that. Let's just, I have somewhat messed up my code. Let's just put that in there. Yep, everything is good. Let's make sure it works. And that version works just fine. I will tell you I don't like this solution at all, but it is important for you to know, especially if you're reading the code from more advanced users, you might see trickery like this. It's common that more advanced programmers will like to golf their code. So in the game of golf, a lower score is better because it's fewer strokes. And when you're golfing your code, you're trying to write it with as few keystrokes as possible, making for very terse code that is actually often much harder to read. So just because you can write something very clever and short, it doesn't make it great, but I do want you to know that you can do these kinds of things. For the next solution, I want to use str.count. So let's just take a look real quick at what that looks like. Here I've got a sequence. Let me grab that. And I can say seek.count of A. And it tells me there's 1. And if I ask for how many C's, it tells me there's 2. That is a lot less effort on my part. What happens if I tell it to count the number of, that was a mistake. I'm just going to try counting the number of X's. It gives me 0. That's great. So what if I were to rewrite my code, that long count function that I have? What if I rewrite it to instead return this tuple? And let's see what that looks like. So open up my DNA and I go down here, and instead of this big long decision tree, I don't even need that. I have now turned my mini line function into a single line. So the fewer lines of code that I write is the better. And nothing changes about the signature, which is that it takes a string and it returns a tuple of 4 integers. Nothing changes about that. The only thing that changes is that I have a lot less code now. Let me show you. First off, let's make sure this still works. I can make test, and this still works. Let me show you yet another way of printing this out and calling this. So let me just take these bits of code, paste them in here. And so now I've decided to go back to unpacking this into 4 distinct values. And now I'm using an F string. So the mnemonic I use is that it's a format string. It's another way of writing a format string, but the F comes at the beginning. And now the variable interpolation happens inside the string. So you don't call .format at the end. The formatting all happens inside the string. So what I like about the F strings is that I can see very easily that count A, count C, count G, count T. I don't have to go back to those arrows that we looked at and kind of visually match it up. I really actually prefer most of the time F strings like this. And in fact, most of the the linting tools that I use will complain if you use format strings. I mean, the format function that prefers you to use format strings. So this is another way to write this, and I will run my test to ensure that it still passes. So this is still a valid way to write code, and I want to stress that too. All of these are valid, and you should stop at whatever solution you feel comfortable with and the one that you feel like you will understand when you come back to your code in a month or 6 months. So that is another way using an f-string for variable interpolation. And here I'm showing that you can do even fancier things inside of these square brackets. They're not just placeholders. They're places where you can actually run code. So for instance, there is a len function, a length, that will tell me the length of a string or the length of a dictionary or a list. And so you can call code inside of there. You can do a lot of fancy formatting of that. You can do, like, padded stuff, zero padded, rounding off of floating point numbers. So a lot of clever things that you can do inside of the format string. Very useful to know. Okay, I want to show you a completely different way of returning the values. I'm sorry, of counting the values into a structure called a dictionary. So this whole course assumes that you know some basics about Python, like how to write functions and what a list and a dictionary and stuff are. So if any of this is leaving you behind, I recommend you go back and go through my material with tiny Python projects. So here I'm going to introduce a really basic dictionary, and then I'm going to show you how to do a lot of very fun, fancy things with it. So the first thing is creating a dictionary, and I always like to go to the REPL. I'm going to call my dictionary counts, and I'm going to create it with curly brackets, empty curly brackets. Another way I could do that is using the dict function. Either way, the type of counts is going to be a dict. So what I'm going to do now, I want to point out first off, if I say what is the counts of A, it's going to blow up because it's trying to access a key that doesn't exist, and that creates an exception, and we see here it's called key error. So what happens is that if I'm going through each base in the DNA, and when it's empty, I've initialized this to be empty, the first time I see a base, it is not going to be in there. And the way to check for that is you say A in counts. This is the syntax in Python for determining if the key called A exists in a dictionary called counts. It's also a way to look for list membership. So we'll talk about that at another point. So this is the way to see, have I seen this in counts? And the way to negate this is to say it's not in counts. So it's true that A is currently not in counts. And if we look at counts, we see it's indeed empty. The way to put it into counts is to simply initialize it. So if I say A is equal to 0, now A is in counts, and if I ask for what is A, for the value of that, it's now equal to 0. And if I want to make that greater by 1, I can use my plus equal, just like I've done before, and now it's equal to 1. And if I just look at counts, then I can see it has a single value of A, and that has been set to 1. If I go through my string and I count and it's all A's, and there are no C's or T's or G's, and I were to try to use this syntax to get out the value of C, it would blow up. So there is a safer way to get a value from a dictionary, and it's called get. So if I say counts get C, it returns what appears to be nothing. Let's put that into, I'm going to put that into result, and I'm going to say what is the type of result? And it is the none type. And so it is true that result is none. This is the proper way to test for none. You could say equal none. Technically that's true, but stylistically you're supposed to use is, res is none. So when get fails to find something, by default it returns none, which is not what I want. I want to return 0. So there's an optional second argument to get of 0. So that is what is going on with this code. Initialize counts to be nothing. If it's true that this base is not currently in counts, initialize the count for this base to be 0, and then this line will always succeed. Increment that base by 1. And then we're going to return we're still returning a tuple of 4 integers, and it's possible that any one of these could fail because I was counting the empty string or something, I was counting protein sequence that didn't have these. So I want to return get that base or 0. And if I take this now and let's see, this is solution, which one is this? Solution 4. And let me go grab this code real quick and go back to my DNA, go back to my count function, paste this in, and nothing else has changed. So this is one of the great things about writing code like this. It's the function itself is a black box. You don't care what goes on inside of it. You only care that the interface doesn't change. It's still passing a string. It's still returning a tuple of 4 values. And so therefore, nothing else about this should fail. So as long as the unit test passes, the integrations test should still pass. The printing still works. The way that I unpack this, it all still works. And that is the point of writing code like this. And then it's also the point of having the test so that you can refactor your code. You can change things around, try to make it better, and you always have tests to go back to ensure that it still works. So this is all what I was just showing you. So let's talk about another way to initialize this dictionary. If we know we only want to count A, C, T, and G, we could initialize this function. We could initialize our dictionary to have just those bases that we want to count. And it now changes the way that we write our loop. We can actually skip over the bases that are not in counts. So for the base in DNA, if the base is in counts, then what we want is to do that. So it shortens our code by a couple of lines, and it kind of tightens it up because we just skip over the bases that we don't care about. It does, however, change what our test should look like, because now when now we're always going to get back a data structure that has the bases that we want, and so we're actually returning now. The other thing here I should have mentioned is that we're changing the signature of our function. It's no longer returning a tuple. It's now going to return a dictionary that always has A, C, G, and T. So it's essentially kind of the same structure. It's going to have those counts for those values, but we're going to return it as a dict. So let's change our function here. So instead of returning all of those, we're just going to return counts. And we need to say that it's going to be a dictionary that goes from a string value as the key, and it's going to have an integer value for the values. And so I'm going to go up here and bring in the dict. I no longer need the tuple, and it's going to change several things about our code. So we're now returning this dictionary, and that means that our test needs to change. So it's no longer going to get back this tuple. So the first thing that we should do is update our test. And for that, I'm going to go just jump over here and grab my test count code. Whoops, that is the... Just a second. I'm going to pause. Okay, so we are using a dictionary here to count only the desired bases, and that means our function, our test function, has to change. And so I was going over here to solution 5, where I have changed the code to be like this, and I want to go back to my DNA and bring in this version of the test count. So before we were testing that it was returning this tuple structure. Now we're testing that it's returning this dictionary structure. So we have to update our function. And this is still broken up here, right? This is still the way that I was calling it before. But I want to point out that I can use pytest right now on just the part, just the test function here. So if I run this -xv on the dna.test.py, I can see that just my test count, it's passing. That's what I want to see. That's one of the nice things about writing unit tests like this, is that I know that the rest of the program is actually broken. If I were to try to run make test right now, then it's going to fail because I'm doing this incorrectly. But I can still see that just the unit test I've written actually works. And you see here, I'm always getting back ACTG. They always have zeros unless there is a value there. And so essentially the test looks almost identical. It's just that the data structure has changed. So that is one of the things that I do point out here in the book, is that if you are writing tests and you're worried about the keys being in a different order for some reason, that here I've defined two dictionaries that have the same content but with the keys defined in different orders, they still evaluate to be essentially the same. So that's a handy thing to know about when you're comparing dictionaries, how they are compared. So how do I use the result of this? Certainly what's going to happen now is you don't unpack dictionaries into individual values. You get back just a dictionary. So counts now is a dictionary, and if I wanted, I could even add some type hint here. This, I know I have a good friend who's a Python programmer, and I think that he would be very unhappy to see this code. A lot of Python programmers really don't like type hints. But this is a way of ensuring that I'm expecting to get back a dictionary with strings and integers, and this function returns a dictionary that goes from strings to integers. And so it is a way of ensuring that I'm getting back from the function what I expect to get back. But the fact is that this type information will now be attached to counts, and programs like TY can track that and use that to help you find errors. Now this part is going to fail because I no longer have these individual variables. So what I can do, I could write it like this. It's not, let's see, let's paste this code. And let me see if my formatter works real quick. Let me create my screen a little bit wider. It is safe in this particular instance for me to call counts A, counts C, because I know I wrote this code. I know that these bases are always going to be present. It still kind of in a way makes me uncomfortable because I know that if something were to change about this function and I didn't initialize these, that this code would now be prone to failing because of a key assertion. But I know for this limited function, because I wrote all this, that this is going to work. So this is another way I'm back to calling a format string, calling the format function of a string and passing in these values. Mostly because I just want you to see many different ways of writing the same kind of code. They all work. And so run make test. Oh, it doesn't like this line. So it doesn't like that this line is so long. And that's fine. If I just want to skip over that, I can just run pytest xv and it won't run the flake. I might actually update that. It's looking for lines that are longer than 79 characters, and I think that Python, the style guide is something like 88 characters is actually considered acceptable. So this is another way to write this, and it works just as well as any other one. Let me show you though, all of this has been building up to trying to get to something called a default dict. So this is one of my favorite data structures in Python. Let me go over here to a REPL and let's import default dict, and let me show you how to use it. So I'm going to initialize counts now to be a default dict that has as its keys anything you want. You typically use strings in Python for the keys of a dictionary, but you can actually use numbers, integers, tuple values, anything that is immutable and can be hashed. Can be the key of a of a dictionary, and that can actually be incredibly useful. I once used latitude, longitude, a tuple of latitude, longitude as the keys in a dictionary. It was really quite useful. So the way this works, why it's called a default dict, is that now if I were to say what is the key value of A, and noticing, let's just look at counts real quick. It is empty, there's nothing there. So if I say what is A, a magical thing happens, is that it it instantiates, auto-vivifies from a term that we would use back in Perl. It creates the key that I just asked for. It doesn't exist, so it gives it a default integer value of 0. That is fantastic because now I can do something really shorthand, like I can say counts at C is plus equal to 1, and now if I look at counts, it has A of 0 and C is 1. Because as soon as I talked about counts at C, it was initialized to 0, and then I added 1 to it, and so now it's 1. That means my code can change significantly down to something like this. So let's go, I want to look at solution 6 now. The first thing I'm going to have to do is I'm going to pull in a default dict. So let me go back to my DNA, and I'm going to bring in default dict, and what's going to happen is in my counts function, it's going to be fairly simple. I'm defining, this still is going to return a dictionary that goes from a string to an int. I'm defining this as a dictionary from a string to an int of a default dict that holds an int. And now my for loop is really quite tight. But what has changed is that I will no longer get back a dictionary that always has A, C, T, and G. It's only going to have the values that are present in the dictionary, in the string that I give it. So that means that my test needs to change as well. So let's go look at how the tests change. Test count now. When I count the empty string, it's going to return an empty dictionary. And now when I count a string that has all these other non-A, C, G, and T, it's actually going to return the counts for those. You may or may not like that. You don't need to, if you have a very, very large string and you only want to count a very small subset of the elements in that, then maybe this would be a terrible way to go about that, because you would be devoting a lot of memory to tracking data that you don't care about. But I'm just showing you how to write a default dict and how you would change the code to reflect that. So now when we count A, we're only going to get back a dictionary that has A as the key and 1 as a value. So given that, this is still up here. This is still going to be broken. But the nice thing, again, is I can go back to pytest, test-xvvx on DNA. I can ensure that test count does indeed work all by itself. I don't need to worry about the integration test. And then I will need to go change how I'm calling this code. I cannot use this code because it will now fail. Let me just prove to myself that it will fail. Oops. It still doesn't like that long line. So, sorry, that should fail. Let me verify that it fails. Oh, you know why? Sorry. this is passing because there is always a, c, t, and g. Let's just run it now with, for instance, this, I'm sorry, I'm going to take a second here. This should fail because I'm calling counts this way. I'm going to pause for a second. Okay, my apologies. I was a little confused here as to why this was working, and it's because I had to be reminded this is returning a default dict. So this will continue to work because even when I ask for the count of t, if it's not present, it will just print 0. So one of the advantages to using a default dict like that. So it is safe to continue to use to get on that, or even to just call it like this. So moving ahead, all of that was really to get you to the point of introducing collections.Counter. And I do love this quote by this author: "Perfection is achieved not when there is nothing more to add, but when there is nothing left to take away." And so to show you this, I'm going to go back to the collections module that we used before. And I'm going to import not default dict, but counter. And for some reason, this one starts with a capital C. And if I use counter on this data structure, you will see that all of the efforts that we've been going through for the last couple of hours can be handled quite simply with this one function. Does all of that work that we did before. To an extent, it's not returning a default dict, but it is returning a dictionary that has all the counts of all the individual elements. And counter works on any iterable, so a string, a list of values, really, really handy function to know about. And it returns something that is sometimes called a bag or a multiset. It is simply the frequency of the items in a list, in an iterable. And the most important thing is that you get this information back without writing any code, which is always the best. So if you know about these functions, then you know that you can skip over a lot of effort in your code. So that means that, technically, we could get our program down to this. So let's get rid of all of this that we've been writing and all of the test-driven development. Very, very cool stuff. But let's go in from collections. Instead of importing that, let's import counter. We no longer need our dict. And now, instead of count args.dna, let's change that to counter. And now we have this code, and we do need to change it because this is going to be a straight up dictionary that will fail with that. Let's change it to this. And now if we go back and run, let's see if we can run make test. If pylint is going to be, it's still not happy about that. Let's just run pytest -xv, and we pass all of our tests. And with this version, we, here, I'll just manually break that. And it doesn't like that. So if I go back to make test, I've now broken that long line. And what we have here is an incredibly simple program that uses counter and then uses this, and we still have our integration test, so we really don't need we just don't need a unit test anymore for counting the individual letters. We have a pretty straightforward program that's easy to read, easy to test, and it works. It completely works. So going further, other things that you could do. So make an input file that has both upper and lowercase text, because that's very common to see. Highly repetitive sections of genomes are often soft-masked as lowercase values. And so maybe your program doesn't want to count nucleotides in soft-masked areas, or maybe it does. And so you have to think about that. So I encourage you to create an input file that has mixed case. Maybe you have an option to your program where you want or do not want to be case sensitive. And so expand your program to handle that, testing it however you want the program to work. And each time you should think about the challenge of writing the tests will really help you focus on how you want to write the interface to the program. Another thing that you could do is incorporate IUPAC codes. So these are other ways that bases could be written. So a lot of times there's ambiguity in base calling, and the calling software is not sure if something is an A or a C, and so we'll use a character to say it could be either of these. And so what do you do with that? How, do you want to count? Do you want to increment both bases? Do you want to just use the IUPAC codes? Do you want to skip over things that aren't A, C, T, and G? I encourage you to think about that. How would you expand this to count protein sequence? Do you want it to be able to detect protein sequences? So, so many things that you could think about. The output of this right now, if it's going to count protein sequences, obviously it's not going to, you don't want to output these 4 numbers separated by spaces. You probably want to create some sort of a table that is each one of the bases, each one of the residues. Do you want to always represent all of the residues and have zeros for the ones that are missing, or do you only want to print the residues that are present? So all of this is up to you. Challenge yourself, come up with other ways that you could write this program and expand on it, and make sure that along the way that you're writing tests. And let's just review for a second what we've gone through. This was really a long chapter. The other ones will most likely be much shorter. But there were a lot of things that we had to go over. First off, we talked about using new.py that helps create a new program, and it accepts and validates all of the command line arguments using argparse, which is just worth it all by itself to learn how to use argparse. It will make your program so much better and easier to use and easier to program if you use that. We got introduced to pytest and how to write functions for pytest, both integration tests and also unit tests. Unit tests are for individual functions, and integration tests are for the whole program. I introduced pylint and flake8. I showed you mypy, but I don't really use that anymore. I've also introduced ty, which I happen to use quite a bit. But, I showed you some instances where ty falls down, like it didn't find that indentation problem. I showed you a little bit about makefiles and how you can alter that makefile there to get rid of those pylint tests. I'm probably going to remove those in the GitHub repository, so that may not be an issue by the time you watch this video. We talked about creating a decision tree with if-else statements. We talked about the many ways of counting the characters in a string, and we landed on collections.Counter being an extremely simple way of counting the frequency of items in an iterable. We talked about how to annotate variables and functions using types. This kind of information here, like the return value of this tuple here having fields also annotated with a type information. We use the REPL extensively to play with code, and I really recommend that you get comfortable with that. We talked a little bit about formatting guidelines for how to name variables, and you have things like documentation strings and indentation levels and such as that. Very important, in my opinion, to follow the prevailing sentiments of a community. So when I'm writing in Rust, I write like Rust programmers. When I'm writing in Python, I try to write like Python programmers. So I think that's an important part of being a good community member. We talked a lot about data structures like strings, lists, tuples, and dictionaries, and how they, especially lists and tuples, how they are similar and how they're different. One of the most important things to take away is that tuples are immutable, and that can be a useful thing. And finally, I did introduce how to use a class, which is the basis for writing objects in Python, but I don't really go further into object-oriented programming. I'm just really using that in order to derive from a base class of a named tuple, and that was important because it is a really handy data structure that that I find to be useful for representing especially the arguments to a program. So there's a lot more to cover, and that is the end of chapter 1.